Okay, so our last section, like I said, we're talking climate change, environmental science. This is probably the main, the lesson that, although I'm not going to give you a unit test, like I'm not going to give you a quiz or a unit test, some of this information will show up on a final exam. So make sure you review this at some point. Much of it you probably already know, and that's one of the nice things about the environmental science section, is that it's not always brand new information to you. It's just putting words to concepts that you've already heard of. So, anyways, let's go through some topics. Today's idea is about climate patterns, and like I said just a few minutes ago, there are some challenges in terms of the science of weather and climate because we can make predictions, and that should really be the hallmark of science, right? A true science should mean that like you know what's going on so much to the point that you can make a prediction and say, I believe that if A, B will happen. Right? For example, like in chemistry, I would be able to make a prediction that if I take a piece of magnesium and I light it on fire, this will happen. Right? And it should happen every single time without fail. You know exactly what's going to occur. Right? Or in physics, if I were to let go of this board, what would you expect to happen? It would fall because you've heard of gravity, right? And maybe I'd even do experiments as to how high it needs to be before it breaks, but I should be able to make a prediction that's always true. Climate science and environmental science is a little more challenging because there are a lot of variables that we haven't fully figured out yet. And so, like I said, when it comes to predicting climate and predicting weather, there are some things that we do seem to have pinned down, but it's not an exact science. Like, for example, I cannot tell you when the next earthquake is going to occur. We don't have that knowledge yet. I can't tell you when the next hurricane is going to hit Florida perfectly. I might make some predictions based on bigger weather patterns. I might even be able to tell you what the weather is going to be like for the next week and a half. But I don't know that I can tell you exactly what the weather is going to be like next summer. Right? But if you've heard of things like, say, like an El Nino or a La Nina pattern, sometimes we have some general predictions. So that's our goal today, to talk about what we do know about weather, but I want to preface it with the knowledge that it's not quite the same sort of science where like if A, always B. It's not. We haven't pinned that down. There's too many variables to know for sure. So let's begin with the first thought here. Different places on Earth have different climates, and we know there are some reasons why. For example, solar variation, latitude, and proximity to water. And this is a reminder of what we talked about yesterday. Energy has the ability to transfer through the biosphere. So quick review, what the heck is a biosphere? It's the fact that we live on a sphere called Earth, and there's life on this Earth. Ta-da! Right? But there's like different parts of the biosphere. Could you guys rename the three main parts we talked about yesterday? Yeah, water, air, and land. What are the like special physics sciencey words for them? Atmosphere for air, hydrosphere for water, and I heard the other one somewhere. Lithosphere? Yeah. So if you didn't catch that verbally, hydrosphere for water, lithosphere for land and rocks, and atmosphere for air. Those are kind of the main ones we'll discuss. If I gave you the word cryosphere, hopefully you'd know that that's like frozen water, like in the tundra, you know, on the tops of mountains. So what we want to discuss today then is, well, why do we get different climates? Why is Earth not the same throughout? Why is Lethbridge vastly different than a rainforest, which is vastly different than the South Pole, which is vastly different than Africa, which we saw in that video yesterday, right? It's one of the things I love about, you know, discussing this is that Earth is not the same. There are some amazingly beautiful places in the world that like are on my bucket list to go travel. I don't know if you guys have started to put together a bucket list in your mind of, yeah, I want to go see that one day. That looks cool. But the cool thing is that it's different. We live in a country, especially in Canada, where Canada has a very, very different climate, even across the one country, right? Vancouver has a very unique climate if you've ever been there. Vancouver is very rainy, but it's also very, in general, very warm. Vancouver doesn't get a whole lot of snow necessarily. Then if you go westward, you get the mountains. Lots of snow if you live on like where I grew up in Cranbrook, BC, which has got like a whole bunch of ski hills nearby. Anyone go skiing in the southeast BC region? You go skiing or snowboarding? Right? So you know the area, like lots of snow there, right? As you keep going west, you get to southern Alberta. And we have a very unique climate as well because although we're temperate grassland, we have Chinooks, which some people, they have no idea what a Chinook is until they come here, right? Where like we have these periods where it snows and then all of a sudden the snow disappears like in a single day, right? And all of a sudden just a warm front of air rushes down off the Rocky Mountains, right? Continue going eastward, you all of a sudden get like the prairies, really farmland, very flat. I drove out with my family to Saskatchewan over the summer, and I mean, boy, if you've been to like just outside of Regina, it is as flat as you can see, right? You get over to Manitoba. Manitoba in Canada is unique because it has a lot of different lakes in it. It has a lot more water proximity to it, which is one of the reasons why Manitoba and Winnipeg in particular is notorious for horrible mosquitoes due to the proximity to so much water nearby. Right? Then you get to Northern Ontario, and Northern Ontario, if you've ever been there, is basically it's rocks and trees. That's it. There's not a whole lot there. It's a long part of the Canadian Shield. Basically huge rock formations, big forests. Right? You keep heading eastwards, you get into the Maritime provinces and through Ontario and Quebec, and all of a sudden it changes there a little bit because they have a sort of climate that allows them to have the deciduous trees, the ones that go through like the green leaves, right? But eventually they'll turn the yellow and the orange and the red, the really pretty fall colors. We don't really get that as much around here, but they get that a lot on the East Coast, right? And we get all of this, and I haven't even talked about like if you go up north and you get to Yukon, Nunavut, but like we get all of that in one country. It's incredible, right? So, anyways, I got on my soapbox because I got talking for a little while here. Let's discuss then why we have different climates, and it really comes down to one word. It comes down to energy. As energy is imparted into these different places in the world, it happens differently. And depending on how that energy transfers depends on what type of climate you have. So I need to give you guys a quick review before we start of the 3 different types of energy transfers: conduction, convection, and radiation, which I'm fairly certain you guys learned in grade 7 or 8 probably. So if you've forgotten them, I've got a slide for each. So here's a quick Cliff Notes review. Conduction is where my 1-year-old accidentally touches the stove, which I don't want her to do, obviously, right? She touches the stove and she burns her hand and goes, whoa, that was hot, right? It's where you literally touch something and there is direct contact between 2 objects, and heat transfers from things that are warm to things that are cold. So you touch the hot pan here, which is why my daughter Cadence, we got to make sure that she stays out of the kitchen sometimes because she likes to reach up on counters and touch, right? So that's conduction. Direct contact. Make sense? You guys have heard of that one before? Sure. Okay, Brett's nodding. Thank you for someone nodding their head. Okay, convection. So convection is kind of how our heating and cooling systems work, where rather than me wanting to get heated up by literally going and touching something warm, we can actually move water or air or something like that due to what's known as a convection current. And what really happens is it's basically due to the concept that warm things rise. Warm air will rise, warm water will rise, and what happens is as it rises, it goes up to the top here. But eventually as it gets further and further up, it cools. And so when it cools, it re-falls back down and it starts to create this cycle. And this is actually going to be a main theme of today's lesson, is many of our weather patterns are based on energy cycling in some sort of circle, where warm things rise and they cool back down. The reason why, by the way, is in this paragraph right here. So if you weren't really sure why hot air rises, it's because it causes things to expand. When you heat things up, they vibrate more, and when they vibrate more, they expand more. Classic example, a hot air balloon. There's nothing special about a hot air balloon other than the fact that you literally take the air that you have there and you heat it up. As you heat it up, it expands, and that decreases its density. And really, density is what helps determine how things layer. The most dense things usually end up on the bottom. The least dense things end up on the top, which is why certain gases end up rising, right? Like, say, helium gas. You guys are familiar with a helium balloon? Right? A helium balloon is one of those ones where if you let it go, it floats away. Now, again, I'll use my daughter as an example. We went to Best Buy once, and they gave them away like a free balloon at the store. And my daughters were so distraught though, because as they got into the car, they had to open the door to get to the car. They had their balloon in one hand. They let go of the balloon, and it floats away. And they go, it's gone, right? And I can't go get it because it's a helium balloon, right? So you feel bad for them. But why does the helium balloon rise like that, right? Well, it's because helium is actually less dense than air. And we actually can do that from chemistry. What is air made of? What are the main components of our atmosphere? You guys remember? Nitrogen and oxygen. On the periodic table, nitrogen and oxygen have molar masses of about 14.01 and 16.00. What's the molar mass of helium, though? Helium's atomic number 2. You probably don't have it memorized like I do, but helium's molar mass is 4. So when you're comparing something that's element number 2, which is a molar mass of 4, to something that's element numbers, 7 and 8? No, it really doesn't compare. It is less dense. There is less mass there. So that's why helium rises. Long story short, hot things, as they expand, they become less dense, just like helium is comparatively, and they rise, but eventually it'll cool back down and form the circle. So that's convection. You guys have hopefully seen that before. Last one is radiation. Radiation is really the main source of our energy, actually. Where does all of the Earth's energy even come from? Yeah, the sun. But the sun isn't touching us, so there's no conduction. And there is no atmosphere between us and the sun. There's literally nothing out there in outer space. Nothing. There is what we consider to be a vacuum. We talked about a vacuum before. It's where there is area and there is nothing in that area, right? So there is no ability for the sun to transfer us energy through conduction or convection. It comes through this third process, radiation. Anything on the electromagnetic spectrum is transferred by radiation. And we get infrared radiation when you stand by a fire. When you're standing by a fire here, you might actually feel the infrared heat, right? Because you're not actually touching the fire. And I mean, eventually the hot air is going to rise and create a convection pattern like this, but it's actually the opposite. You feel the heat coming this way, but hot air would actually cause the convection pattern to rise upwards. So you're actually feeling radiant energy in the form of infrared, a form of heat. And really what ends up happening is when this energy is absorbed, it actually causes an increase in temperature. This, by the way, is the key principle behind what we know for sure about science and global warming, is that when you input in any sort of electromagnetic energy that's radiant, it causes molecules to vibrate. And I got a few slides on this. First, I've got a slide reminding you guys of what the electromagnetic spectrum is, because I believe, again, you've learned this at some point in middle school. You guys remember talking about radio waves, infrared rays, visible light, ultraviolet X-rays, and gamma rays? Typically, infrared is the one where heat gets transmitted, and here's the reason why. Okay. Carbon dioxide is the most common greenhouse gas we mention. It's not the only one, but it's one of the biggest ones that gets discussed. Here's what happens. This is what a carbon dioxide molecule normally looks like. There's a carbon in the middle, and there's 2 oxygens on the outside, hence the carbon dioxide. And what happens is, when one of these waves comes and hits it, certain wavelengths, only certain wavelengths, get absorbed by it. And it causes this bond to basically bend. So imagine that it was supposed to be straight across. So I have my finger straight across here. What's going to happen is, as a wavelength hits it, it causes it to bend back and forth like this. And what ends up happening is that energy from the sun causes this molecule to basically absorb that energy. And I like this graph right here. Here's a graph of all of the possible spectrum of light. So that goes from radio to infrared to visible to ultraviolet to gamma. Okay. What happens then is certain materials will absorb certain wavelengths. And so carbon dioxide right here seems to be absorbing this particular wavelength right here. Carbon dioxide doesn't absorb this one, or this one, or this one, but unfortunately it seems to absorb infrared, which isn't a good thing. Because you guys remember from last day we talked about the idea of a net radiation budget, where the Earth is supposed to absorb some energy, but reflect off other energy, and there's a fine line there. We want to absorb this much, not too hot, not too cold. We need the Goldilocks zone, right? We need to be right in the middle there. There have been times in Earth's history where we've undergone ice ages, where Earth has been a little bit too cold, and ice has literally covered the whole world. Well, scientists are worried that maybe we're going to absorb too much energy. Okay. That's what we know for sure. That we can explain by science. That we can always predict and model. And so that's basically the concept here, is that due to certain wavelengths of light getting absorbed by these molecules here, it causes them to bend and kind of vibrate back and forth, and that vibration means that they've now absorbed that energy. Not through the process of convection or through conduction, but through radiant energy. That make sense? Cool. Okay, so now that we've talked about the three main ways that energy can move, conduction, convection, radiation, now we want to discuss, well, how do we get different weather and climate on the Earth? Why is it not the exact same everywhere? And there are many reasons why, so many reasons that it's very challenging to predict. Right? I got to be honest, I think weather people, they do a pretty decent job, but there are some days where, like, it says it's supposed to be cloudy and it's sunny, and they say it's supposed to be sunny, and all of a sudden there's a freak rainstorm, right? Like, they're not perfect, but they do a pretty good job. I need you guys to know the difference between the two words here. First one is weather, and the biggest thing about weather is always short term. We're talking today or tomorrow, but basically we're discussing in the very, very near future. Like, today's weather looks like it's slightly overcast, but probably going to be kind of sunny. Right? And we can discuss things like temperature, whether it's going to rain or not, whether it's windy or not. You guys know humidity? You've ever heard that word before? Like, that's how much water is in the atmosphere. Whether it's going to be cloudy or stormy, how much air pressure there is. That's weather. That's a short-term phenomenon. In general, because it's short-term, we're okay at measuring weather. Climate, though, is a long-term trend. And we're also relatively good at knowing trends. Like, for example, I am probably going to predict, I'm not going on a huge limb here, but the summer, next summer, 2019 summer, I bet you it's going to be sunny. It's not a huge limb there, but I've learned something in the years I've been alive, is that summers are usually warm and winters are usually cold. I know, groundbreaking here. Slow down. But that's the thing, right? Like, right now, is this winter right now, has it been particularly snowy? Okay, that is weather, not climate. Climate means that in general, long-term predictions would normally have us know that it's usually snowy in wintertime, right? I don't know about you guys, but I'm just kind of expecting that any day here it's going to snow. Although, my personal preference, by the way, I always like it when it snows on the last day of school, when we, like, finish for Christmas break. And we get a nice big Chinook on, like, January 7th or so. So that, like, for, like, the 2 weeks that we're off, you can go skiing, tobogganing, all that stuff. And then afterwards, it's gone. Oh, I love that, if that's what happens. Anyways, you guys get what I'm saying, I hope, right? Where, in general, climate is a long-term trend, but weather is what it is on a day-to-day basis. Okay. Now, we know about some of these long-term trends due to seasons. And one of the biggest reasons why we have seasons has to do with Earth's tilted axis. And this was mentioned yesterday in the video quite a bit. So if you're not really aware of how this works, I want to spend some time discussing why we even have seasons. Okay. This is one of the best pictures I've seen to describe this. Earth is actually not straight up and down. Most of the time when you guys see a globe of some type, north is up and south is down and east and west are on opposite sides. That's actually not how it works, which seems crazy because that's just how you see it every single time. But north is actually slightly tilted compared to where we are on the sun. If the sun was over here, north is actually like on a bit of an angle over here, and south is on an angle over here. And it really depends on when in the year it happens to be. In this particular time of year, this is probably what we experience as winter. And the reason why we're experiencing winter is that up here in the northern hemisphere, somewhere up here where Lethbridge is, we don't get a lot of sun. And the reason why is we're slightly tipped away from the sun, whereas the southern hemisphere is actually slightly tipped towards. So if you guys didn't know this, right now it's actually summer in Australia. Right? Like on the other side, like on the southern hemisphere, it's actually currently what they consider summer. I've never been able to wrap my head around this because we always talk about, like, at Christmas, Santa is always like in his snow and stuff like that. I think it would be very strange living in like a southern hemisphere place where we talk about winter as, you were in Australia, right? Yeah. What do they do for Christmas down there? Like, it's not snow-based, right?
So many backyard
Barbecues, right? But that's like for us, that's a summer thing as opposed to a winter thing, right? Is Santa still a like a snow kind of mythical creature? Santa is a beach bum in Australia. Seriously? That's so cool. Yeah, I can't wrap my mind around that because I'm doing Santa with my little girls right now, right? And they're all about snow and reindeers in the North Pole, right? But like right now on the other side of the world, it's a completely different climate. Yeah. So why is it a different climate? Just to make sure we're clear, it has to do with the tilt. Okay. Now this picture right here, why don't I have a better picture of this? Okay, I need a better picture. I thought I put one of them in here. The reason why, I need to maybe draw a new one here, is that we know that the sun is at the center of our solar system. So give me a second to draw a really good sun here. I'll give them sunglasses too, because every sun is supposed to have sunglasses on it. Okay, so there's our sun, right? When the Earth is over here, and it's tipped like this, north to south, we are currently experiencing winter because you can see that the sun's rays take a little bit further to get here than they do to get here. Can you see how there's there's a little bit of a difference there? But due to a further distance away, for us, this is winter. And for them, on the other side of the world, it's now summer. Other side, I mean the southern side of the world. However, when the Earth rotates around the sun and goes in its big circle around, eventually the exact same thing happens. The tilt is still the exact same way, and now north is slightly closer than south, and so now it's actually easier for you to get rays to the north side than the south side. And that explains why we have seasons, because as the Earth kind of goes around like this, in a picture here, this is our summer, then there's fall, then winter, then spring. I'm just doing this with my grade 9s right now. Have you guys heard of the words solstice and equinox? An equinox is basically in the fall and the spring where you have equal days and nights. And the solstices are either in the winter or the summer. So hopefully you guys were somewhat aware of that. That is one of the biggest reasons why we have different climates is that, and it's not the only reason, we have so many more to cover today, but one of the biggest reasons why is different amounts of solar energy depending on the time of year. Okay. So I've got some more pictures here to kind of reference what I've discussed. But yeah, the climates exist because it's not the same amount of solar radiation. There is one thing unique though, is that if you live around the equator, the sun hits the equator more or less dead on though. So like if you are living more or less right about here at the equator, it really doesn't matter what time of year it is for you. It's almost always warm, which is why the tropic zone, remember how we talked about like there's 3 different zones? The tropic zone right in the middle around the equator, it's almost always warm there. Now what really differentiates those then is one of 2 things. Do I need to close the window? Is it getting in your eyes now? If you live in the tropics, the question is it a desert or a rainforest? If it's a desert, it means you have no rain. If it's a rainforest, it means you do have rain, right? So the Amazon rainforest is characterized by a lot of rain, and the Sahara Desert is characterized by not a lot of rain. Okay, here's another picture to kind of illustrate the same concept here. Have I covered this well enough that you get the concept here? Can I move on? Okay, so I got pictures here in case you want to look at them. This talks about your seasons here for a bit. Here's one more picture to kind of illustrate how much sunlight you get. Let me talk about this picture for a second, actually. Can you see how all of these squares right here, they're all kind of describing the same like amount of sunlight in the same sort of like incoming amount? However, the fact that the Earth is curved also makes a bit of a difference. Can you see how right here, although the Earth is curved, see how it's not like overly curved comparatively? Whereas at the north and at the south, it's quite curved. Here's why that matters, is that the same amount right here of sunlight has to cover more territory, but here the same amount of sunlight has to cover less territory. And what that means is that everybody around the equator gets more energy because they don't have to share it so much. Can I say that again here? Right here, these guys down here, the same amount of incoming energy has to get shared over more territory due to Earth being curved. But right here at the equator, it doesn't have to get shared quite so much, which is why there's so much energy at the equator. One of the stats we heard yesterday in the video was that I think over half of the life forms on Earth are found in rainforests, yet they only take up 3% of the Earth's territory. It's incredible how much sunlight they get compared to like northern climates. Okay, next topic. Why else do we have different weather patterns? What else causes there to be a difference in climate? Another one has to do with atmospheric pressure. Okay, so a bit of a science lesson first. We have to know what atmospheric pressure is. There is air around us. You might not be able to see it, but in southern Alberta, we can feel it. When you get hit by wind, what do you really, when we feel wind, what's really happening? Well, air particles are hitting you, right? Here, I can do this. I'm hitting you with air. You don't really notice it all that much, right? But if I do this, right, like I'm making air move. Sometimes you might even make like a fan and go like this. Now I might notice it, right? But all you're doing is making air move. There is atmospheric pressure. There is air around us. And because of this, we're going to talk in a second about the concept of wind and how wind is able to move from areas of high to low pressure. I want to describe why over the next few slides. First, though, I want to talk about this picture right here. What we know is that closer to the Earth's surface, there is more pressure due to a stronger force of gravity. You guys know how, like, when you get into outer space, there's no gravity anymore, right? The reason why is the further you get away from Earth, the less gravity seems to take place. So what ends up happening is there are a lot of air molecules really close to the Earth's surface. And as you go further up in altitude, there's less of them. It's one of the reasons why if you ever climb Mount Everest or go in an airplane, you have to bring oxygen with you because there's very, very little air the further up you go. So they even have to they have to make sure that airplanes have pressure. They have to be pressurized cabins so that you actually have enough air to breathe. And it's why the first thing that happens when there's a problem, if you're in an airplane, those little masks come down. You're supposed to put the mask on yourself first if you've been on an airplane before. So let me go to my next slide here. This describes high to low pressure systems. And climatologists, those who work on trying to study weather patterns, if you ever watch the weather person, right? You see the H's and the L's on the weather screen. Those are high and low pressure systems. High pressure systems means that you have a lot of air molecules here, and they want to spread out. So all of these particles here, they would like to basically, diffuse. You guys remember the word diffusion from biology, right? These particles, they want to spread out as much as they possibly can. A low pressure system usually means kind of the opposite. So a low pressure system means that there's not quite as many particles there. And usually what ends up happening is high pressure systems are usually coming down, low pressure systems are coming up. But the more important thing is that wind always travels from high to low because you have a lot of particles here, a lot of air, carbon dioxide, nitrogen. Hey guys. And all of this right here, the high pressure system, wants to move to an area where there's like a vacuum, where there's something missing, right? When we talked about diffusion in our biology section, if I were to spray a thing of perfume on one side of the room, slowly but surely it would spread itself out. High pressure. Nope, no test on this. Project.
Look, actually, gentlemen. This is the look that we've got from every class we've walked over. Wednesday first block.
Bill, you used to be a weatherman, right?
Bill used to be a weatherman.
Yeah, we're talking about weather and climate.
My first degree is in meteorology. I was a forecaster. If you mean by weatherman, someone on TV.
He wasn't on TV.
Interesting thing.
I mean, someone who actually forecast.
When Bill was young, he was on a milk truck.
I was.
We are talking about weather and climate today, Bill. Yes.
I recognize the high and low pressure.
Yeah.
And the clouds. And the sun.
Okay, so here's another picture. Did you guys want us, or are you just hanging out?
Did anybody see the short video on some
Thanks, man.
social media that had, you gotta find this,
Okay.
that had a guy
Shh, stop.
blow a soap bubble and then blow smoke in the soap bubble and then on top of it light a flame, and it created inside of his soap bubble a smoke tornado
Cool.
as it burned at the top of the smoke bubble. I'm not kidding. It was like last week. We're doing that.
Okay, we'll have to
You might
YouTube
think
that in a bit here.
science, it's actually. Chris, we have to try that.
Well, we were discussing earlier today the challenges of trying to predict weather and climate and how, because really that's magic, I think.
Hey, everybody, have a very good day.
There might be someone in this class who might be confused by this picture because they spend a lot of their life in the southern hemisphere.
We've already discussed that
So
today.
just make sure
We've already discussed
you
that.
understand this is here, okay?
Just stand on your head, upside
Look
down.
at it the other way. I know it's kind of confusing, but we go with this here.
See you, Chris.
Thanks, guys. Have a great day.
I'll see my
What's that? Did you find it? Oh, cool. As soon as I'm done this, let me find the link and I'll put it up on the screen. He's already found the YouTube video. Okay, so here's another picture describing the same thing. All I need you guys to be able to know is what way does a wind travel from high to low, right? So you can kind of see right here, a high pressure area has a whole bunch of extra pressure particles, right? There's more density to it here, and it wants to naturally diffuse outward from high to low. Okay. Now, here's another thing that we in general have picked up on in terms of climate science is that in general, temperature is lower at higher altitudes. If you go to the top of a mountain, it is cold up there, right? Now, that actually seems counterintuitive because wouldn't you actually be closer to the sun? Yeah, and that seems backwards. Do you gotta go? Oh, okay. Yeah, when you're further up in altitude, you'd think, well, you're closer to the sun, shouldn't it be warmer? But it actually has to do with the fact that there is less air there to work with, and so heat can't transfer as easily through convection currents, right? Because how is air moving? It's moving through these convection currents going up and down and up and down, and there's less of it up here, right? There's more air. Let's go back to this picture here. There are more air particles, even though you can't see them near the surface of the Earth. There are less further up, so therefore it's harder for energy to transfer higher up, right? And if energy can't transfer higher up in general, it is warmer down here, and it's colder down here. There's also one more reason why as well. On the surface of the Earth is stuff. I don't care what the stuff is, but there is stuff on the surface of the Earth, and it can absorb energy. Remember how we talked about that whole infrared absorbing concept? Like, say you get into your car in the middle of the summertime, and you have leather seats, and the leather seats are just warm, right? They're sticky, right? Why are they so warm? Well, because they've absorbed energy through radiant energy. Okay. Here's a word I need you to know, though. It's actually possible to have what's known as an inversion. Inversions are kind of where the opposite happens, where it gets stuck. Normally, we expect the cold to be at the top and the hot to be at the bottom. But in an inversion, you actually get a cool layer up top, a warm layer in the middle, and a cool layer at the bottom again. And actually what ends up happening is all of the cold air stays down at the bottom. We actually see this sometimes in the bottom of the river valley. You ever see like a fog kind of down at the bottom by the river, by the bottom of like the Old Man down there? That's probably some sort of inversion where a lot of cool air is staying trapped down near the bottom. And we're seeing that cold air because it's all water droplets that are starting to condense into, well, like a fog. Okay, next topic. This is what Bill is actually trying to jazz you about here. It's called the Coriolis effect. And another unique factor that Earth has is the fact that it rotates. Earth doesn't just move in a stationary pattern around the sun. It actually spins on its axis as well, which is why we have days and nights. It takes 24 hours for the Earth to spin. Because of that, we get some weather patterns due to Earth's just natural spinning around in a circle. Okay. Now, before I get to that, though, I do want to discuss how there's actually some natural winds that occur due to the fact that the North Pole is in general fairly cold, and it's fairly warm down by the equators. In general, what will happen then is cold air will want to come from the north and go towards the south. Why will it do that? Well, it's because warm air, remember how warm things rise? The warm air by the equator is going to want to rise. It will naturally then go towards where it's cold, and then the cold air will try to come back to where it's warm again and then rise. So cold things condense, contract, and go down. So long story short, in general, what ends up happening is there are some winds that go towards the south. if you're in the northern hemisphere. So, Taco, if you're in the southern hemisphere, sorry, I won't jazz you anymore on that. But if you're in the southern hemisphere, winds in general tend to go from the South Pole towards the equator. So they actually tend to go north before the hot warm air rises and then eventually comes back and falls. Okay. But because Earth is spinning, it screws things up. Okay. Earth is always spinning. And so in general, what's happening is if there's supposed to be a weather current that was, say, supposed to be going this way or was supposed to be going this way, but Earth is now spinning, it actually causes it to deflect off to the side, and it goes one way or the other. In the northern hemisphere, it starts to deflect in this sort of circular pattern. And so it always goes what we call clockwise. But what's weird about it is that in the southern hemisphere, it actually goes the other way. It actually spins in a counterclockwise pattern. The classic example, it's not technically the Coriolis effect, but if you flush a toilet, in theory what ends up happening is the water is supposed to spin one way around a toilet. And in the southern hemisphere, it actually spins the other way. There was a Simpsons episode about this years and years ago, but you guys probably, anybody watch The Simpsons, or is that way too dated of a reference? Watch The Simpsons? You know the one where Bart goes to Australia, has the collect call? Okay. One person gets it, that's worth it. So, does this make sense? Can I explain this one more time? Because this is really key. This is a big part of why our weather phenomena exist the way they do. Okay. Let me go back and show you 2 slides back to back again here, because I want you to understand this. We know that warm air rises. Warm air rises. So as the warm air rises, it cools down. There's less density up top. And so if you were standing right here, you're on the, well, don't stand in the water, obviously, but if you're standing right here at the equator, warm air is going to rise. And if you are up here at the North Pole with Santa, cold things are going to contract and condense. It means that right here and right here, we have a difference between a high and low pressure system. Ooh, let's talk about it. Which one is high, which one's low? It always goes from high to low, so therefore the air is going to travel in a circular pattern like this. Right? However, if air, we now believe, is in general wanting to travel from the North Pole to the equator or from the South Pole to the equator, just like this, from the North Pole to the equator, from the South Pole to the equator, Earth is spinning. Right? And as Earth is spinning, it causes it to deflect. So rather than going in a straight line like you'd expect it to, it actually starts to go in this sort of direction in the southern hemisphere. That direction is counterclockwise. In the northern hemisphere, it actually goes in a clockwise direction. And it creates what I've got on this slide right here. I'm going to come back to the one I skipped. But it creates what are known as the trade winds. There are some very natural flowing winds that historically sailors would use to try to get different places. We often call them westerlies. And the reason why they're called westerlies is that because of that deflection, remember how we said that it was normally supposed to go this way, but it's getting deflected. You can see that right here, there's a lot of winds that are going this way right here. And this way right here is to the west. And the same thing happens in the southern hemisphere. Winds were supposed to go this direction here, but they get deflected this way. And so there's often a lot of winds that are always traveling to the west. Talk about historical context. North America, okay, granted, settled by Aboriginal people a long time ago, but in 1492, when the first European ships came over, this is the principle in which they were able to travel, is that there are a lot of winds that are ending up in Central America due to this pattern here, which is why that's kind of where Columbus ended up at, is down in this area down here. That makes sense? Due to those west traveling winds. Now, what actually ends up happening is, technically, it's more than just like one big wind heading towards the equator. What ends up happening is some air goes towards the equator, and eventually it just picks back up and goes higher up again. And then this wind actually goes the opposite direction, and then this wind goes that direction. There's actually like a couple of different weather current patterns. So there's not just one big one. There's technically some like smaller in-between ones, but the same thing more or less happens, right? Hot air will rise, the hot air will move, it will condense and create these patterns here. Hot air will rise, oh, hang on. hot air will rise, go this way, and cool. And so it creates these convection currents. That's the word I need you guys to know, convection currents. It creates our winds, basically. So even though it's supposed to be going north-south, it gets deflected one way or the other, depending on whether it's going clockwise or counterclockwise. Okay. Really important, because not only did that carry ships, but it carries our energy. Okay. Let me go back to the slide I skipped here. This just, once again, shows the same concept here. In general, if we're intending to go one way, it's actually going to deflect you off the other sides there. I think I've covered that well enough, though. Okay. There's actually another way in which wind travels, or energy travels as well. They're called the jet streams. And the jet streams are not on the surface of the Earth. They're way up high in the stratosphere. You guys remember from last day, we talked about the different parts of the atmosphere. The stratosphere is quite up there. And there are actually some wind patterns that are fast moving air, known as the jet streams. And we actually use these for air travel. If you were to travel from New York to London, if your airplane can get inside of a jet stream, these things actually travel over 250 miles an hour. And that's actually one of the reasons, for any of you who've maybe done long distance travel, it actually takes longer to travel this direction than it does to travel this direction. If you were to travel, like Melissa and I, we went to Halifax one year. It took us 4 hours to go from Calgary to Halifax. It took us 5 hours to go from Halifax back to Calgary. And I'm not talking about time changes, I'm just talking about how long the flight was. And the reason why is that in one direction you're traveling with the jet stream, and in the other direction you're traveling against the jet stream. Has anybody ever experienced this before, where they've done like a flight two different directions and it's shorter on one direction than the other one? That's why. It's due to jet streams. So this is not wind, by the way. There's not like a big current of air that we feel going through like Canada right here or going through London right here. This is up in the stratosphere up there. Okay, another thing here. We need to also discuss water, because although wind can move energy around, so can water. And so the difference between this picture right here, which if I erase some of the stuff that I drew on top, see how in this picture right here, there's lines all over the globe, but very specifically, there are lines that are on top of land as well as on top of water. Okay, that would be air in the atmosphere. But in the hydrosphere, there are also currents that we've discovered based on just water moving. Now, sometimes, I wrote this down here, sometimes they match up. Sometimes the path that the water is moving is also the same path as which the wind is moving. That would make a lot of sense. But it's not always the case, because air is going to behave differently on water than on land. And so you can also see that in general, there are some really well-known ocean currents, not the wind, but we're talking about how the water itself has warm and cold current patterns. If any of you have seen the movie Finding Nemo, right? They talk about like the pattern here that takes you from Australia. So pretend Australia is down here, right? And it's supposed to take you, up here to North America, right? They talk about that with the big sea turtles and stuff like that, right? So these are some well-known weather patterns, and you'll notice that many of them also seem to go in a circular direction, right? In the southern hemisphere, many of them seem to be going in a counterclockwise direction. In the northern hemisphere, they tend to be going in a clockwise direction. Why? Because the Earth is spinning, right? And that Earth spinning causes things that normally want to go straight to go a little bit veered off to the side. Okay, we're getting close to the end here. Thank you for staying with me, by the way. This is a long topic here. Near land, we've also discovered some phenomena that, again, we can regularly predict, right? We kind of recognize these over time. They're known as land and sea breezes. And this picture here hopefully will kind of describe how this works. Land, in general, does a really good job of heating up. There is a lot of stuff on our land. We've got asphalt, we've got buildings, we've got trees, we've got grass. In general, when radiation comes from the sun and it hits our land, in general, that absorbs. In general, that will absorb energy. Sometimes it reflects it, but a lot of it absorbs. Side note. What absorbs more, white or black colors? Black absorbs more colors, actually, yeah. White is actually a better reflective surface. Okay. Now, here's why this matters. In the last 100 years, we have, in general, probably done a pretty bad job of emitting carbon dioxide. But you know what else we've done in the last 100 years as well? Is we've built a lot of stuff, especially buildings, and especially roads and parking lots. And when we compare how much absorption roads, parking lots, buildings, how they have compared to dirt and rocks and trees and stuff like that, yeah, that's a great way of putting it, right? If you ever try to walk on asphalt when it's really, really hot and bare feet, right, it's going to burn, right? Whereas it's not quite as bad on grass. What I'm trying to get at here is, in the last 100 years, in the last century, we've built civilization as we know it, right? But that civilization also absorbs more energy than it would have if it would just been left to nature. Does that make sense? Now, I'm not trying to come across as like global warming is not real. I'm not trying to say that at all. I'm just trying to point out that that's a really, really good thing to mention, is that as we build more stuff on the surface of the Earth, it causes more heat to be absorbed. Now let's get back to land and sea breezes. If we agree that there's a lot of absorbing heat during the day, what ends up happening is, as we've learned, warm air rises. Well, when you're out at sea, and if you live near a body of water, well, as that warm air goes out to sea, it eventually cools back down, and it creates this circular pattern here. So typically during the day, what happens is you get what's called a sea breeze, where the breeze is coming from the sea towards the land. And anyone who lives, like, we don't get this in southern Alberta because we don't have a lot of oceans or lakes, but like Vancouver, anything on the west coast, they experience this a lot. However, it's different at nighttime. At nighttime, all of a sudden there's no more radiant energy coming in because the sun is gone. So there's no more radiant energy coming in, right? Which means that you have no energy here. However, here's something really useful. The ocean stays relatively constant in its temperature. And so even though during the day to night, like for us, say, like, you know how we have like a high and a low temperature? The daytime high of 22 and the nighttime low of 3 degrees, it's going to definitely cool down right here on land. But the ocean actually stays relatively similar temperature, so it actually becomes warmer in comparison. Gotta make sure I emphasize that a lot. The ocean will now become warmer in comparison. It's actually not warmer. It was the same temperature all along. It's just this goes from being hot to being cold. And so if this is now warmer, it now has its hot air rise go this way. And you actually get what's known as a land breeze, because now the air is going to rush back out to sea. So you actually get competing winds when you're on like the docks. If you live nearby somewhere where there's docks and there's an ocean nearby, during the day, air comes towards the land, and during the night, air goes away from the land. And that's actually one of the really big principles behind basically why we're so concerned about global warming, is that if we're going to absorb too much heat, well, then what are the side effects of that? Right? So what I want to explain to you guys these 3 days is, what do we know for sure about science that we can make predictions on, and then there are predictions out there for global warming, some of which have come true, some of which have not come true. Well, that's what I want you guys to do the research on afterwards. Does that make sense? So I got a couple last pictures just to illustrate it again. The sea is warmer in comparison. So it goes in this direction here. Or during the day, our stuff on Earth absorbs so much energy, that radiant energy from the sun, we absorb it, that eventually warm air rises and causes the pattern this way. Last thought. Sometimes what we'll end up doing is we're going to want to record different climates. So now that I've given you some things that, just some basic climatology, things that we are able to use to hopefully predict weather and climate patterns, sometimes we want to visualize that. And one of the ways that we visualize it is in what's called a climatograph. This will definitely be on your final exams. It's not hard, so I'm not feeling like I need to give you a quiz on it. All you got to be able to do is basically just read the graph. And there's always 2 things on the graph. There's always, behind the graph, there's always like a bar graph, and it talks about how much rain or precipitation there is. And then there's always another graph that talks about how much temperature there is. And basically, you want to be able to look and see how they compare to each other. So here, let's start with this one in Australia. Since we've already discussed Australia today, and we have a... Are you still considered an Aussie? You can see that in terms of like their temperature, when is the warm time of year in Australia? Well, the warm time of year is in January, December, right? They have their cold months during June, July, August, right? But they also have the opposite for precipitation. I'm assuming that most of this precipitation here is kind of like how in winter we're going to get like some snow and rain. That must be a wet season. In what we consider summer, on the other side of the world, they're considering it to be like a wet season. Okay, so here's some more. This is Vancouver. Take a look at Vancouver. It goes through a really classic seasonal change where there's cold in January, warms up in the summer, and then cools back down again. But how does Vancouver work for precipitation? Well, they get a lot of their rain during January, February, March. They don't get a lot of rain during the summer, and then they get more during the winter time. Let's compare another one. This is Medicine Hat nearby. And you'll notice that it actually has a very similar pattern. See how this one's opposite? See how this goes down while this one goes up? That explains why Vancouver has a very different climate than Medicine Hat. Because in Medicine Hat, again, the temperature goes up during the summer. This is the summer here, May, June, July, August. Temperature goes up during the summer. But when is most of the precipitation? Also during the summer. There's a lot of rain during the summertime. There is some snow here and here and here. But in southern Alberta, do we get a lot of snow? I mean, sometimes we do. But like, doesn't it, we go through a lot of Chinooks, don't we? Right? Where generally, year after year, if we do get some snow, it goes away fairly quickly, right? So this actually somewhat makes some sort of sense that the rain and the temperature, they follow each other. This is Halifax. And Halifax has, again, a bit of an opposite pattern. Again, Halifax has a summer during January, July, August, but it has a more consistent rain pattern. Although there is more of the rain in the winter months, it's actually very, very similar. It's nowhere near as drastic. And one of the reasons why it's so similar is that Halifax is closer to the ocean. And the closer you are to the ocean, the more likely you are to be part of the water cycle, the raining effect, right? Because when you're near the ocean, there's more water to evaporate, and then that evaporation can then cause it to rain again. We don't get a lot of that because we don't have any bodies of water nearby. Here's the last one I want to show, and then I think I'm done. This is in Peru. What do you notice that's kind of weird about Peru compared to all the other places we've talked about before? Yeah, look at the average temperature. It is, it's not moving. The average temperature is always about 26. Where is Peru found? By the equator. And what did we learn about the equator? The equator always has the same amount of sun. Yeah. They don't have seasons in the same way we do. We get, summer, winter, fall, spring, right? But in a lot of places in the world, especially in tropical climates, they don't have seasons. It's always the same temperature. What they do get, though, is a wet season and a dry season. Right here, it seems like right here seems to be a wet season, and this seems to be a dry season. And so sometimes they only get two seasons, wet, dry, like monsoon season, dry season. And again, why would they have those changes in weather patterns? Well, like we discussed here, the main concept is all about convection currents. Whether it's water or whether it's air, like this picture right here. Air is going to be moving around from high to low pressure systems. And in doing so, it creates a convection current that moves energy. Depending on the geographic conditions nearby, that kind of affects why we have different places on Earth. Okay, that was a long time there. You guys have any what questions do you guys have? Does that make sense? Was that stuff that you'd kind of heard before as well? It wasn't brand new information? Okay, so that's all I've got for the day. There's no assignment, so there's really nothing for you guys to go home and work on, except if I handed you out a progress sheet that had all your stuff on it, and there were some gaps on there, can you guys take some time and finish those up? Okay, I know you might have handed something in, by the way, and I just haven't marked it yet, but can you make sure sometime in the next few days that you've cleaned that up? And by the way, if you still haven't done anything for physics or for chemistry, can I get those as well? It's in your best interest, I think, to have the 3 progress logs for 70% of your mark done. Even though you can replace it with my final exams, it's probably better to have done all the work along the way. So, you guys good? Okay, if you want to, throw your name on the board and go work somewhere else. Or stick around, it's up to you guys.